Good morning, guys. We are going to start on three-phase synchronous motors. And the first motor that we're going to look at is the three-phase synchronous alternator. Up to this point, we've looked at three-phase synchronous, alternators. And three-phase synchronous alternators have the exact same construction that a synchronous three-phase motor does. It's being used in the opposite direction. So the stator construction is the same, where we're going to have our poles spaced 120 degrees apart between phase A, B, and C, and our rotor as well ends up having our DC excitation and derives its DC excitation the exact same way, where there's a small DC generator on the shaft that goes out to a three-phase bridge rectifier and then out to the shaft. So there are a few subtle differences that I will mention and bring up, but other than that, it should be fairly straightforward. One big thing with these motors is which are on obviously the other motors, but isn't normally talked about, is a amortisor winding. So an amortisor winding is what helps these motors get up to speed and start moving. Obviously, when we had a prime mover with an alternator, that's what spun the shaft and got the shaft spinning. But in this case, what ends up getting it going is an amortisor winding. And amortisor winding is basically a squirrel cage. So a squirrel cage, if you've seen if you've seen a blower motor inside a furnace, or even like a little hamster wheel, is basically what the construction of the amortisor winding looks like. So when I have my rotor in the center, and the rotor has salient poles on it, right? Those poles protrude out all around the rotor, and they have the coils of wire around it. This amortisor winding sticks over top. And this amortisor winding has aluminum bars, and they're typically, or it can be steel bars, and are typically welded together with a solid ring on each side. What this does is it gives a path for current to flow through those bars. So when I end up turning on my DC excitation, before I turn on my DC excitation, I'm going to have my three poles on each side. So I have the phase 1, phase 2, phase 3, and obviously I end up from that getting a rotating magnetic field. And that rotating magnetic field simply comes from the power that is supplying that machine. So I've got 60 hertz of power on all three of these. Those produce, they're all 120 degrees out of phase with each other. So this one's going to see power slightly before this one, which is going to see power slightly before this one, and it's going to keep going 60 times per second. And that spinning of that rotating magnetic field is going to induce current into these bars, and if you look, that's a completed path for current to flow. Another path for current to flow, another path for current to flow. And if I end up having a path for current to flow through those bars, I end up getting a magnetic field that is created around it. And that magnetic field reacts with the magnetic field that is being brought around it, and you're going to find that amortissor winding starts to spin, and that's what gets that rotor initially spinning. However, the problem with this, and as I'm sure you've seen in class, when I start the motor up, it only gets it to almost synchronous speed. So it gets it up to maybe in the lab, 1792 RPM, somewhere around there. It's maybe 5 to 10 RPMs less than what my synchronous speed is. That value might be 96 to 98% of synchronous speed, but it can't quite get there. The reason for it not being able to get there is that if this amortissor winding and that rotor ended up getting to the exact same speed that the rotating magnetic field was at and was able to maintain that, well, now I'm not having bars which are conductive. I'm not having those bars being cut by lines of flux anymore, because they'd be going at the same rate of speed. So because I wouldn't have lines of flux being cut, and I still need to drive this motor and this shaft, that motor is going to be slightly out of step or slightly slower than that rotating magnetic field all the time. So because I'm not driving a load, it doesn't have to be a lot, but it's basically, it gets almost up to synchronous speed and just it tries to get there, but as it gets close, it ends up losing the current through those windings. It loses the magnetic field that is in that rotor, and it begins to slow down again, and so it ends up resting at around that 1792 or 96 RPMs. So I don't get, or I don't have relative motion between the rotor and the rotating magnetic field if they are going the same speed. And in order to get that motor moving, I need relative motion. So it has to be slightly slower at all times. So that amortissor winding is around, and so I would end up having, just kind of glob them in. I've got my windings from my salient poles, which would be all on the inside. And those bars would be interconnected around those windings. Everything's neat and in one little place. So that amortissor winding is ends up being the sole thing that gets that motor almost to synchronous speed. So at that point is when we end up turning on our DC excitation, and our DC excitation, as we had said before, it comes from a three-phase little generator on the shaft. Right, so we had DC, two DC little poles with a magnetic field going around it. So those three-phase windings are on the shaft, maybe, or on the shaft inside. So those are your three-phase windings, are here, back here. So the shaft would come out, and those windings would be located around the rotor, off of the head of the rotor, and then I'd have my little DC power supply on either side. So I'd end up having my plus and my negative, and I've got I've got the coils rotating within that magnetic field, induces a three-phase voltage into those windings. And then it ends up going through that three-phase rectifier, as we said, and then probably filtered through a capacitor and then out to the head where I get my my strong magnetic field. And then at that point, when the DC excitation is turned on and I have a strong a magnet, that's when you get that little bump in the lab where it ends up pulling it forward, and that's where it gets pulled into step or into synchronism with the rotating magnetic field. And as you know, in the lab, that is 1800 RPMs, and that is determined based on the frequency of the applied voltage and also the number of poles. So last time what ended up determining the frequency was the speed of the prime mover, and the poles end up giving you the frequency output. Now we have a set frequency, we have a set number of poles, and that's what ends up giving that motor the speed that it ends up having. Let me erase that. And same formula. Frequency is equal to Pn divided by 120, or you'll see a lot of times PS for speed, but N technically is speed divided by 120. And so now we have our set frequency that we know is 60 hertz. Those machines in the lab are 4-pole. So we want to account for N, or solve for N. That's 7200 is equal to 4N. So I just multiplied by 120 on each side. That gets rid of that, which gives us 4N. Divide by 4 on each side, and we get our 1800 RPM. One note, just while I am thinking about it, for test purposes, any motor that is, and I know this doesn't seem like a lot, but any motor above 500 RPM is classed as a high-speed motor. So I gotta link this to with code. It would be 500 RPMs and above, or greater than 499 RPM would be a high-speed motor. So 500 and above it should actually be. So put a little star beside that in your notes. A lot of smaller motors end up being air-cooled, and the larger motors, so this would also apply to the large alternators, are cooled by nitrogen. So large synchronous motors cooled by nitrogen. Let's make a note about that. And I will try to trick you and say, oh, it's hydrogen, but obviously you wouldn't want hydrogen in case in a motor where there's can be arc in that, because obviously you'd end up having a large boom. So large motors are cooled by nitrogen. So as for starting up a synchronous motor, we've talked about the amortisseur winding that gets at the speed. We've talked about the DC excitation, which ends up locking it together. And then that motor is going to run at synchronous speed. And these motors, and also induction motors that we talk about later, are all classed as are all classed as constant speed motors. However, the synchronous motor technically will always stay at synchronous speed. So no matter what, a synchronous motor, doesn't matter what the load is, to a point, that motor will always stay at synchronous speed. And when I say that it'll only stay there to a point, if I end up adding a load that is too large, so it exceeds the torque limits or the power output of that motor, or what it's able to drive, it will eventually pull apart. And I like to think of the truck and trailer example, driving down the road, towing a trailer behind you, and as that trailer is being towed down the road, it's got an elastic band between the trailer hitch of the trailer and also the truck, and someone keeps throwing rocks into the back of that trailer. So as the load, starts increasing in the back of the trailer, that elastic band is going to start to stretch as the weight gets bigger, as it starts to draw backwards. But even as that weight increases, that truck is still going to be able to pull it, but they're going to get further and further and further apart. But between adding load, that trailer is still going to be going at the same rate of speed as that truck. Eventually, though, I'm going to strain that elastic band so much that it's going to break. And at that point, once they pull out of step with each other, then that trailer obviously will fall to a halt. That's the same as with a synchronous motor. Once that rotor is pulled out of step with that rotating magnetic field, it ends up stalling out and coming to a halt. So make note of that when a synchronous motor is loaded down too much. It will actually get pulled out of step completely. So constant speed motor until I exceed the limitations of that synchronous motor. The lab that you're going to end up going through this week is looking at the synchronous V curves of a synchronous motor. So what this is, you're going to look at two little V's, these V curves. And this is the main thing I want to get through in this video. So the one on either side, this is going to be our current. So current. So this would be current. So high current, low current, and this is going to be so high, low current, and this is going to be in my line conductors. So how much that motor is going to be drawing, and this is going to be excitation current. Where our center point is going to be our let's do normal or nominal current. So normal. So this point right here is going to be the amount of current that is required to keep the rotor magnetic field and the rotating magnetic field locked together. So when we end up starting up the motor, that motor ends up, getting almost a synchronous speed. Then we turn on the DC excitation, and when we turn on the DC excitation, they lock together. And then typically, once we're at that point, they're locked together, we dial back that DC excitation. Make sure you can see everything here, so I don't get in trouble again. I turn it down a little bit, so I start at 1.5, and then I turn it back to 1, and that motor runs. That's going to be roughly what I'm meaning of our nominal or normal excitation current. I've got an area over this side, which is our underexcited, and I've got over here overexcited. So when I over excite my current in this motor, when I overexcite it, I end up getting a decrease. So this is going to be here, our power factor. I want to make note of that. So that's going to be our power factor. So when it drips or droops down on each side, so we can also say, so this is also power factor. There's two little things in one. Power factor low, power factor high, but the power factor relates to the curves that are going down. When I overexcite my excitation current, and to overexcite it, I just add more DC excitation on that rotor. So I increase my rotor current. I end up finding that my power factor ends up going down. So it ends up dropping right off. So this is going to be unity power factor is going to be here. So if I have a high power factor, it's going to be a value of 1. So when I'm at a normal excitation current, I have a power factor of 1, and I have very little current that is drawn by my motor. So this is the lowest point, and that would be the normal current that would end up being run. I'm not sure how much of this I'm going to get into as to the reasons in this video right now. We'll see how I feel about that. But we've got normal excitation current has power factor of 1, which is obviously the best you can have, and we have a low line current. When I begin to overexcite, so that would be increase my field excitation current, I end up finding that my power factor goes down. If my power factor goes down, and obviously it's going down in either direction, it means that I have what being added? Well, if my power factor is going one way or the other, or being more poor, it's going to be either more capacitive or more inductive to have a bad power factor. I need a reactive load being added. And if you notice that as my power factor goes down, I'm saying I'm having something added, some type of load added, and it's an additional type of load added to that motor. And as that load is being added solely by overexciting it, I see that my current begins to go up. It begins to get higher. And you might even see, I don't know, an increase of 4 to 5 amps as it goes up. Well, what we find is that when we overexcite it, it becomes more capacitive. Okay, I know that's kind of weird, seeing that it becomes more capacitive. And then when we go to underexcite it, and I come the other way, my power factor gets poor again, and also my current begins to go up. We find that when it's underexcited, it becomes more inductive. So the neat thing with these motors is they are also called a synchronous condenser. And as a synchronous condenser, what I can do is they end up being able to be used for power factor correction. I was at a job site one time, or it was a industrial building, and there was a motor in the middle of one of the rooms, and it was running, and there's nothing connected to it. It's just sitting there running, and I had no idea what it was used for, and I was like, that's strange, why is it just running there? And didn't really think much about it. Came to school, came to advance, and learned about synchronous motors, that they can be overexcited in their field current and can be more capacitive. So I'm not sure how much you went into it. Obviously in intermediate you have talked about power factor correction. So if you have a load that is more inductive, in order to offset that to come closer to unity power factor, I need to add a capacitor or capacitor bank into that field. And as different loads end up being added or taken away, capacitor banks need to be also added for a high inductive load and taken off for a low inductive load. Well, a synchronous motor can be adjusted to allow for all those. So let's say, I'm not having a lot of changes in the shop, but I end up, having a few motors running, and I want power factor correct for the utility, so my bills end up being a lot cheaper. I can take a synchronous motor, I can put it in, and I can adjust that field current up a little bit. And, when I adjust that up a little bit, that capacitive load that it ends up having ends up offsetting the inductive load in that circuit. And then let's say I want to add another inductive load into the motor. I can again adjust that DC excitation, and I can make that synchronous motor more capacitive to end up offsetting that. So the nice thing is I don't have to bring in more capacitive banks or larger capacitor bank. I can just adjust that DC excitation slightly more, and it also offsets for that additional load that's brought in. So very important. The biggest thing from this, and even when I go to explain the reason why, I don't want you to take a whole lot from it except for just this, that when I have normal excitation current, my power factor is at unity, which means it looks like a resistive load. My current is really low. When I overexcite it, it becomes more capacitive, and obviously if it becomes more capacitive, my power factor goes down and current goes high. When I underexcite that field current, my power factor goes down, which that current is inductive. So the current goes up, that is inductive, and that obviously ends up adding a greater inductive load into that circuit, or more of a draw that way. So make sure that's in your notes. One thing I do want to say though, with factor correction is a lot of old shops have motors that have, you know, a very poor power factor on the motor. So let's just say I had a motor that was at 75%, and let's say it was 10 amps. I'm not going to go through all the math, but let's say it was 10 amps. Obviously, I can add in that. Synchronous condenser, that synchronous motor, and offset it. But even if I, let's say I want to add in a new motor, or one of the motors in the shop, I just want to, put in a new induction motor. I could install an induction motor, let's say it was a 10 amp draw as well, and that motor was, had a power factor of 95%. Just adding in a motor with a better power factor is going to improve the power factor. It doesn't just have to be adding a capacitor bank or adding in that motor that has, or the synchronous condenser. I can just put in motors that have better power factors themselves, and it will offset the power factor that's actually in that room. Or, putting in more resistive loads will also improve the power factor, because it's the true power. So resistive loads over the apparent power. So if I can end up improving that power factor as a whole, doesn't have to be with capacitors, I'm going to end up going a lot further with correcting that power factor in that specific building. I'm going to try to just at this point explain what ends up happening in the most simplistic way I can for overexciting and underexciting for those synchronous V curves to get them more capacitive. So let's kind of look at it as this is going to be our pole here. This is going to be a north. And we've got our rotor magnetic field that ends up, our rotor magnetic field that's whipping past. Okay, so we've got, this is our rotor, and this is our stator. Okay, so rotor's about to whip past. A synchronous motor likes to have innately a certain amount of magnetic field or magnetic lines of flux in this air gap. So let's just say it likes to have that. Alright, so I've got a magnetic field. Let's do the same number. So 3 going one way, and that is the magnetic field from the rotor, and 3 going this way, and that's the magnetic field created by the rotating magnetic field. And remember, this is spinning and this is stationary. So that motor wants to run at a specific amount of speed. Let's say I go to increase, increase the magnetic field of the rotor. So I go to overexcited. What ends up happening is, and I think think I tend to say what ends up happening quite a bit. I also say and so as a little connector word to connect stuff together. Hopefully that doesn't make my videos more annoying. I'll try to stop that. I increase my magnetic field in the rotor. Creates more lines of flux from the rotor, and in doing so, my magnetic field from my rotating magnetic field will end up decreasing. So let's say I had 6 lines of flux, so 3 one way, 3 the other way. When I increase the magnetic field in the rotor, the magnetic field produced from the poles ends up decreasing. The magnetic field produced from the rotor ends up being used to strengthen the magnetic field. So it isn't used just to push the load. It is only used to magnetize. And that extra current that ends up being produced on that rotor ends up having a leading power factor rather than a lagging power factor. So it ends up having a magnetizing effect. And when it ends up happening the other way, so this is capacitive. Okay, so that ends up having a magnetizing effect, and that current leads the magnetic field produced from the poles in the stator. When I end up going the other way though, let's bring these all back, and I weaken this magnetic field. Let's do our 6 lines, and we've got 1, 2, 3. So this is what we started with. And I go to weaken this magnetic field, which means I have less lines of flux coming from this way. I have 1. And let's do this one actually. So now I only have 1 line of flux going the other way. When I weaken this magnetic field, I mixed that up. When it's the other way, it has a demagnetizing effect. So this one has a demagnetizing effect, the first one, demagnetizing, and it's more capacitive. When I'm doing this one, I only have 1 going the other way. And this current that is created has a magnetizing effect. So the other one is demagnetizing, make that known. This one is a magnetizing effect, so I end up, all the current, excess current that is being brought in to strengthen and push that rotor to keep it going the exact same speed and to keep those, the rotating magnetic field and the rotor locked together. All the current that ends up coming in is being brought in to strengthen the magnetic field. And when that extra current is brought in, that current to magnetize is inductive. It's inductive current. So in the first one, the extra current, so in the capacitive state, that extra current from the field winding, when I overexcite it, that current demagnetizes, and when it demagnetizes, it is more capacitive current that ends up coming in. When I'm going the other way, and I weaken this one in order to strengthen it, the current that comes in is more inductive because I'm trying to create more magnetism to push that. So not only do I have to drive the load, but then I also have to strengthen that magnet, and it is more inductive because I'm trying to add to the magnetic field that was there, where the first one I'm trying to counteract the magnetic field. So that's how I get more of a capacitive or more of an inductive power factor. So nothing too crazy. I'm not going to ask you specifically about demagnetizing and magnetizing. The only thing I'm going to ask you about is those synchronous V curves. And those synchronous V curves, they have a high power factor, which is a unity power factor, more resistive at a normal excitation current, and my current's low. As I overexcite it, I get a bad power factor because the current that's coming in is more capacitive. And when I go the other way and I underexcite it, my current goes up again, and that current that's coming in, as I said, I'm not going to require you to remember this, is to strengthen the magnetic field, and it's more inductive. So just know those curves, and when you do the lab, it'll make it'll make a lot more sense for you. Just trying to think for the one more thing I'm going to talk about, and then I'm going to end this video off because I know there's quite a bit of information that was in this video. So remember I was talking about how when I've got the truck, start to fall a little bit. I was talking about loading the trailer down and that that elastic band stretching as load is brought in. Excuse me. I end up, still being able to do work. I still able to pull the load, but obviously that elastic band is getting strained more and more and more. So I'll just relate that back to in a motor, synchronous motor. So I've got my pole with my windings on it, and I'm going to have my rotor, stator, and my rotor. So I've got a magnetic field, kind of starting in the same way. Got magnetic field going this way, or my lines of flux going this way, and I also have my lines of flux going back in the other direction. These lines of flux that go in this direction are created from a voltage and a current going through these windings and through the pole, producing that magnetic field. So as the current goes through, the magnetic field is produced. So I've got a EMF, so a voltage that is produced, a specific voltage that is produced, and a specific current that is produced. This rotor has a magnetic field, and that magnetic field is also going to be acting upon, because it is spinning, even though we say they are synchronous, they are spinning. That magnetic field is also going to be cutting through those windings in the opposite direction. okay? Or sorry, it's going to be cutting through at the same time, but the magnetic field from the rotor, why I said other direction, is it ends up producing counter EMF. So an electromotive force or a voltage or force in the opposite direction to the voltage that created all of that in the first place. So I have my EMF or my voltage, my supplied input power, and then I also have one that counteracts it. So when I don't have a load on the shaft, they are perfectly lined up, and the voltage or my EMF and my counter EMF are directly opposing each other. Okay? As I end up adding a load to my shaft, what ends up happening is I get a shift. So my rotor, instead of being completely at those poles, and remember this is spinning, so rather than technically being slightly behind, is actually slightly lagging the rotating magnetic field. But what we end up getting is a rotor simulation of the rotor where it is now pole behind or almost strained like that elastic band. So now those magnetic lines of flux that had those created from that EMF are now going to be going here, and those lines of flux coming from the rotor are like that. They might be a little distorted or trying to pull at each other a little bit, but now that counter EMF is not directly opposing the EMF from the rotating magnetic field. When that happens, I end up being able to get more EMF and more current flowing, so with more voltage ends up being more current flowing through my stator windings. And if the current in my stator windings ends up going up, I end up producing more power, end up producing more current. So this here is referred to as my torque angle. As load is increased, the angle between my rotor and my stator begin to increase, and I end up getting a greater torque angle. I wouldn't be able to draw or drive more load if I wasn't being able to produce more torque, and I won't be able to produce more torque unless I have more current flowing through these stator windings. So in order to drive that shaft to strengthen the magnetic field, because now they don't fully line up, so once I can have more current flowing through there, I can produce more torque. So the greater the torque angle, obviously the more torque that needs to be produced by that motor to drive it, and because I have a lot larger load as well, I need more power to drive it. So that's where that comes in, is I end up having this torque angle between the two, and the greater the angle between these 2 points, the greater the torque needs to be in order to still drive that load, and that is in relation to that load. So as the load gets bigger, the torque angle gets larger in order to have more current flowing through those windings to produce a stronger magnetic field in those stator windings, and that's why my current goes up as I add load, because more current is now able to get into these windings, but needs to get into these windings to end up driving that heavier and heavier load. So that's all I'm going to talk about with Synchronous Motors this morning. Hopefully everything makes sense. I'll talk to you guys in class. And if there's anything that wasn't clear, I'll go through that. And you guys have a test on Wednesday. And then there's a bunch of math stuff I want to get into too with the Synchronous Motors. Okay, so that should be everything. So I'm gonna put a bunch of content. I'm going to add another video. You can watch it if you want. It's the same type of video as the last one, just shows you the operation. However, it is that annoying, as you were saying, male Siri voice in the background. And I might also midweek, I may put another video up, or I might just do a longer one next week Friday. Okay, so enjoy the rest of your day.